Right. Welcome to the final session of the day for StrimziCon. So we have the final session for the day is leveraging tiered storage in Strimzi-operated Kafka. And we have Lixin Yao, Bo Gao, and Vrishali Bhor here to chat about that. So throughout the session, if you have any questions, please put them in the Q&A, and we should have some time at the end to ask some questions. So with that, I'll hand over to you.
Okay, thank you. Hello, everyone. My name is Lixin Yao. I'm a software engineer at Apple. Today, Bhor, Vrishali, and me will talk about our story of adopting tier storage feature in Strimzi-operated Kafka at Apple. So here's a brief agenda of our talk today. We will start with some background and motivation on our architecture, why we are interested in tier storage feature, and then we will walk through our journey of integrating the tier storage feature and share some lessons learned during our integration. We'll also talk about some number on performance benchmark, and then share more about our team's contribution with the Strimzi open source community. I will leave the rest of time for question and answer. Okay, hand over to Vrishali.
Okay. Thanks, Lixin. This diagram here illustrates our typical ingestion pipeline for streaming applications. It showcases the flow of data from left to right. On the source side, we have data coming in from multiple sources, and that includes hardware devices as well as server-side log events. This data is ingested through a gateway service. Gateway service acts as a crucial entry point into the ingestion pipeline. It performs several functions. It provides a security check by ensuring that only authorized data enters the pipeline. It verifies the integrity and quality of the incoming data. It also conducts schema validation by using schemas from the schema registry. And finally, it serializes the data by converting it into a format more suitable for Kafka consumption before writing it to Kafka. On the consumer side, Apache Flink is a widely adopted choice for streaming applications. Flink applications consume the serialized data from Kafka and use schemas from the schema registry to deserialize it accordingly. Following deserialization, Flink enriches the data with additional business logic, making it more valuable and contextually relevant. Next, please. Now let's take a closer look at the Kafka clusters in our ingestion pipeline. We use AWS EKS for all our workloads, including Kafka. EKS gives us a standardized Kubernetes environment and makes it straightforward for us to install Kafka. To install Kafka, we use the Strimzi Kubernetes operator. We use Strimzi because it simplifies running Apache Kafka on clusters. We manage Strimzi and Kafka deployments using Helm. For storage, we use EBS volumes. They have been reliable since day one, even though they are a bit expensive. To expose the Kafka endpoint to external clients, we use Nginx Ingress Controller. Now, besides Kafka, we also use other tools from the Kafka ecosystem. We use Burrow for reporting lag metrics. We use Kafka Manager UI to give us an interactive view of the brokers and topic information. We also use cruise control for resource tracking and anomaly detection. This setup gives us a robust, scalable, and efficient data streaming architecture. Now, in our use cases, we often need to use multiple Kafka clusters for an ingestion pipeline. Each Kafka cluster has its own dedicated namespace, but these clusters can be in the same EKS or in different EKS environments. We install one instance of Strimzi operator per EKS. This operator manages all the Kafka clusters within that EKS. The Strimzi operator watches all the namespaces in the same EKS and therefore allows us to streamline our operations. This deployment model has significantly reduced our overhead involved in managing Kafka clusters. We have been running this Kafka architecture for quite a while now, and overall, it's been performing great. However, we have encountered some challenges, particularly around cost management. Initially, we used IO1 volumes, which delivered excellent performance, but they are quite expensive. To save costs, we also experimented with GP3 volumes. While this helped, the costs were still high and became a significant concern. In some use cases, the concern was more than the others. For example, some applications require 1 week of data retention period. The associated costs with this can be prohibitive, and that's where the tiered storage feature comes in. It allows us to move large amounts of data from expensive storage like EBS volumes to more affordable options like S3. This shift addresses financial concerns, enabling us to offer longer retention times without breaking the bank. Performance wise, moving data to remote storage hasn't caused significant issues. For most use cases where consumers need latest data, performance remains unaffected because the most recent data always stays on the broker disk and remote reads are quite infrequent. Additionally, reducing local storage volumes has improved cluster reliability. Scaling the cluster for higher traffic is now easier, either by adjusting retention times or adding more brokers. Broker startup time and replication times have also improved. In addition to this, tiered storage has also reduced our operational overhead significantly. Previously, extending retention times during outages required temporarily expanding persistent volumes, and this is a non reversible action. Post outage, we would need to migrate traffic back to a standard sized cluster, which again is a complex process. With tiered storage, that is no longer necessary. We can adjust the total retention times without frequently altering local EBS volumes. This largely simplifies our operations and reduces overhead. To summarize, tiered storage has allowed us to manage costs effectively, improve performance, as well as streamline our operations. Over to Bo.
Thanks, Vrishali. Let's look at the journey of our tier storage integration timeline. We have a brief timeline here for that. We kick off our efforts with reaching out to Satish, who is the author of KIP 405, starting from February 2023. We got a lot of help from Satish to get the project bootstrapped with his private dev branch in 2.8. We also get a lot of help from Alan guys, who is engineering team trying to actively working on open source their remote storage plugins in S3. In the prototype phase in April 2023, we were able to start 2.8 Kafka cluster with a remote storage layer on S3. Then we spent a lot of time on functional testing, performance tuning, and other type of testing. We also built our own internal version of S3 remote plugin with some customization and optimization for our use case. By September 2023, we were confident with the 2.8 dev branch Kafka, and we consider it verified and ready to deploy. But it's still built upon a private dev branch and have some limited support from Kafka community. So we also noticed there are many new fixes and improvements merged into the trunk in the past few months. With that, we only offer this version as a special addition to our internal customers. In the meanwhile, Kafka 3.6 was also getting close to release, so we decided to take the trunk branch and then take the 3.6 branch for another round of testing. So the rationale is that even though 3.6 is not declared as production ready, we can still get some basic functionality working and get active community support since then if we find issues. So besides tier storage feature, moving Kafka from 2.8 to 3.6 is also challenging. There are many incompatible issues surfaced, which we can talk about more in details later. But all in all, by November 2023, we were able to sort out all kinds of challenges and verify 3.6 Kafka with our internal remote plugin implementation. So we have since then gradually rolled out that version to our production smoothly since then. So looking a little bit deeper down, let's move on to talk about some technical challenges. At the beginning, we decided to try the Dev 2.0 branch Kafka. It's pretty challenging task because our team doesn't have experience building Kafka and Strimzi. We were just relying on public release, the Strimzi operator and the Strimzi Kafka image in deployment. Fortunately, we can the documentation for Strimzi is really good, and with some trial and error, we were able to build Strimzi, including both the operator and the Kafka image. Another challenge we faced was that how can we include the remote plugin library into the Strimzi build Kafka image? The plugin library was not part of the Kafka repo, so it's not included in the tar file generated by Kafka build. We have two options. One is that we could customize the tar file in Kafka build and use a composed tar file as input for Strimzi build. However, this option is not ideal because everything we want to change, every time we want to change the plugin library, we will need to rebuild Kafka and through the rebuild Kafka and rebuild Strimzi, which is time consuming and error prone. So the other approach we choose that is that we customize the Docker image directly with additional library for remote S3 plugins. This way works because it doesn't require the rebuild of Strimzi every time. We only make changes to the remote plugin library. So we have documented this instruction as example in Strimzi proposal document for tier storage support. So the other one is that after we got a working image, we need to ensure all the new tier storage related configuration can be configured correctly and passed down to Kafka broker. We were able to pass everything via Kafka config in Strimzi API. It's working, but not ideal. We have thereafter make a Strimzi proposal to support tier storage natively in Strimzi to simplify the configuration, and we'll cover that later. So in this tier storage feature, we need a plugin library for handling the remote storage metadata. We use a default implementation using a Kafka internal topic to store remote log metadata. The plugin comes with Kafka directly and is ready to use out of the box. In the plugin implementation, a new internal Kafka client is created to read and write the internal topic. We need to configure the necessary configuration for this Kafka client and make sure its connection is secured. So after talking with the Strimzi owners, we decided to use the internal client to talk to 9091 port, which is a reserved internal port exposed by Strimzi for inter-broker communication. The client can establish MTLS connection with Kafka broker using Strimzi created key store and passwords. So as mentioned before, we have 2.8 dev branch working and verified, and we decided to explore 3.6 Kafka directly to ensure we are up to date with all the recent deployment work from the community. This requires us to revisit our build pipeline. First challenge is that we start to use Java 17 now for the build. So we need to experiment a much newer Strimzi version 0.38 to fit the 3.6 Kafka version. The rebuilding process seems smooth, but we soon realized that there's a new Kafka cluster is not able to establish consumer SSL connection consistently. With some of the digging into the Strimzi and Kafka release history in the brute force style, we notice a suspicious issue in Strimzi release node. So that is related with ingress controller dependency version, which is caused by a slightly TLS behavior change in Java 17. If you have also see the similar issue, then probably we can provide some of the information to save your time. So at this point, we're able to get the Kafka cluster start up and running healthy. However, there are still a lot of challenges when enabling tier storage feature. Initially, we were not able to get a consumer fetching from remote store consistently. Occasionally, the consumer could be stuck with no obvious reason. With some research, we find that the trick is that we need to tune the max fetch wait time to ensure the consumer have enough wait time to wait for the remote store to get the data back. This is because remote fetch is happening, the broker side latency typically increase a little bit. So sometimes we got P99 latency for S3 GET API that could reach a very high number, like a few seconds. So we need to increase this number and instruct the Kafka client to wait a bit longer. After increasing the configuration value, we were able to get the consumer application running consistently. Another interesting configuration to consider tuning is the remote log reader threads and remote log manager thread pool size. It's kind of case-by-case varying in our testing, but increasing the thread pool size and the reader threads, we could see slightly performance improvements. The other one configuration worth mentioning is the log segment size. The log segment size decide the segment file size saved in Kafka, and the file size will be uploaded to remote storage and fetched down from there. So if that number is too small, you will end up with a lot of metadata information and a lot more S3 or like remote store fetch and upload. But with that number became too large, then the payload will become very large, and then the S3 API call will have some latency, and that have a latency implication as well. So let's go to the next slides. Okay, so at this point, we're able to achieve basic upload and download. However, the performance is still not up to the expectation. We did some optimization in the plugin library. So first one is we use a multi-part upload for upload paths. So the multi-part uploads allow you to upload a single object as a set of parts. So each part is a portion of the data, and you can upload these object parts independently without any order. And if the transmission of any parts fails, you can transmit or you resubmit. After all the parts has been submitted to the remote, you can instruct Amazon S3 to assemble these parts together to create the original object which you desire to upload. So in our case, this is a perfect case for multi-part uploads. Second part is that we use the AWS S3 range fetch API. So the behavior comparisons before is that instead of use a single thread fetching, we were able to use a thread pool to parallel fetch and speed up the fetching performance. And you don't need to fetch the entire thing if you only want a certain part of the segments to be fetched. So in our test, we enable this multi-parts upload and concurrent range fetch that improve our performance a lot. In terms of bytes in and bytes out, we observe the throughputs roughly 5 times comparing with before. So now we're in a relatively good state. The next step is to do the performance tuning. We're able to have a healthy Kafka running. We're able to perform remote fetch and upload in a decent performance. So we spent some time to do the testing for various test cases. For example, what would happen when we have many consumer applications consuming the same topic from the earliest offset altogether? In our test case, we noticed that the broker could become very busy and cause interruption to other basic functionalities. So basically, you have a noisy neighbor. For example, the Kafka producer client will start to experience very high latency, and per broker bytes in may get impacted. So the remote upload functionality is also affected due to lack of CPU cycles. To mitigate this issue, we choose to adjust the thread pool that fetch threads use from a cache thread pool to a fixed thread pool. So the previous one, the problem with a cached thread pool is that it will create up to maximum integer number of threads, as it always spin up a new thread if there's a new ask. So however, the fixed thread pool it will have a clear upper bound on the thread numbers to avoid exhausting all the CPU resources, so you don't become like the bad neighbor and consume all the threads which could be used by the producer. So the fixed thread pool have this limitation that we only have certain number of threads to use. With some of the tuning, we're able to find an acceptable solution for that. Another optimization we use was that we choose to create two separate thread pool for the fetching logic and upload logic in the remote storage manager. Initially, we mix all the functionality with a single thread pool in the idea that both of that resource could be shared for both fetching and upload. But then we realize they're affecting each other sometimes. So to provide a guaranteed upper bound or a lower bound of performance, we separate them so that the thread pool are managed separately, and we're able to ensure separation of both of the function. So here I would like to share some of the numbers for benchmark perf testing. In the test cases here, we set up Kafka cluster with 6 brokers, each of them running 3.6 Kafka. We use Strimzi version 0.38 to manage Kafka clusters, and each broker is running at R5N4 large EC2 AWS instance. Each instance have 16 CPU and 64 gig memory. We use this perf2 provided by Kafka for testing. For each of the topic, we set its partition number to 48 and replication factor S3. The test case, during the test case, we force the consumers to fetch from the earliest offset. So in this case, we're going to make sure that all the consumer is triggering the remote fetch pass. So let's look at the numbers. So the result, the key metrics we monitor is a per broker bytes in and bytes out. So that's what we highlight here in this table. Here we compare 3 different cases. First one, a single consumer and a single topic. With the given setup, we can achieve, I think, it's 270 megabytes per second bytes out. This number is close to the perf we can achieve without any remote fetch. So it's looking good. Second one, we slightly add more consumers into that. We don't see a lot of big change in the performance number, but slightly drops because I think maybe the complexity of the different consumers have some implications. So we see the similar performance at broker level, but per broker consumer level, we see should be roughly around 80 megabytes per second to 100 megabytes per second. Last one is that we include more consumer groups, and we bump the topic numbers to 400. So this time we can see increasing topic numbers could cause implication on the performance. In our case, each consumer can get a bit less, around 20 to 30 megabytes bytes out. And this becomes a concern for our use case. You may want to do some additional tunings and optimizations to improve the perf for a larger amount of topics. I think the key bottleneck here is mostly related on CPU. So when we are using a bigger EC2 instance, then the bottleneck has been relieved, then we see a much bigger number as well. But that's wrap up the performance benchmarking for this.
Okay, now I would like to move on and talk about some open source contribution we have made. Like we mentioned before, we work closely with Strimzi maintainers on a native tier storage support proposal. So this is available after 0.40.0 release. In this proposal, we are able to group all the tier storage related configuration into a dedicated tier storage spec and a Kafka spec. The users are able to specify the class information for the remote storage manager, as well as some additional configuration for remote storage manager. So the Strimzi implementation take the assumption that the remote log metadata manager will use the default option, like what we do in what Bhor talked about, which is a topic-based remote log metadata manager class. So this configuration for remote log metadata manager class can be simply omitted, and those necessary configuration and all the internal client configuration we talked about before will be automatically generated and passed to Kafka broker configuration by Strimzi cluster operator. For the configuration in the previous slides, this is the final configuration generated by Strimzi cluster operator. There are 3 sections generated. The first part is ILMM config generated by Strimzi. So this contains the basic setup for the feature enablement and the ILM client configuration. The second part is remote storage manager configuration set by the operator and by the user. The additional configuration value, for example, the bucket name is placed here. The third part is if there's any additional configuration for the custom IOM config, it will be placed here. So please note that the support in Strimzi is only for configuration. So to make the feature work, you still need to include the library dependency into the Kafka library, like for example, using the approach we talked about before. Here is an example how we do this using the Docker. So we simply put the prebuilt jar file into a dependency folder, and the folder path is predefined at the remote log storage manager class path. In this way, the Kafka can identify the plugin library class and execute the task. If you are interested to know more about the implementation or the proposal, you can find additional information in this reference link. So that's all I have prepared for the talk. I would like to take questions from audience.
Thank you very much. Really interesting to see kind of the different levels, and then yeah, great that we've got this now being contributed back into Strimzi as well. We don't currently, I don't think, have any questions, but I did have a question for all of you, which was in your experience of then engaging with the contributors, what would you recommend for people who are also interested in contributing to Strimzi? What did you find were the kind of easiest ways to engage with the community and make progress?
I want to call that I get really warm welcome from the community, especially from Jakub and Paulo. So they give our team very strong support and guidance on the implementation. So I think it's when we reach out, so I think the response and the level of support we get is really high. So I would say if other people want to contribute to Strimzi, definitely reach out. And there are, from what I learned, there are some open topics that need help on implementation, and they also have some good idea on some known feature improvement we need to work on. So I think the level of support from maintainer is definitely exceed my expectation. So thank you, Jakub and Paulo, for all the support.
Yeah, based on my experience, it's also very responsive. It's really fast actually, the response cycle. Once you reach out, pretty much within a day or so, you're gonna get some response, and then there will be further instructions, and they will give you a lot of useful links to follow up. I think that's very responsive, which is indeed surprisingly in a good way.
Awesome. So yeah, if anyone does think of any other questions, then feel free to put them in the Q&A in the next few minutes. Also, all of our speakers are available as well in the Strimzi Slack channel, so you can go over there and ask them any questions as well. So yeah, thank you again for speaking today.
Thank you for hosting.
So with that, that is actually the end of StrimziCon. So the last thing that we wanted to do is a massive thank you to the Cloud Native Computing Foundation for not only accepting Strimzi as an incubating project, but also helping us to host this event. We wouldn't be able to do it without them. They provided the whole platform for this. So yeah, just a massive thank you to CNCF for taking Strimzi in and helping us to run StrimziCon as well.